Every time a generation thinks it has seen the most extraordinary thing that rocketry can produce, SpaceX finds another level. And what Elon Musk just revealed about the upcoming first ever Starship upper stage catch is not another level. It is an entirely different game. Because what is coming has never been attempted by any organization, any government, or any engineering team in the entire history of human spaceflight. Not even close. To understand why catching the ship is so fundamentally different from everything that came before it, you have to start with a number. 17,500 miles per hour. That is the velocity at which the Starship upper stage arrives back at Earth after reaching orbit. Not descending from a high altitude like the booster does, not slowing down from a controlled hover, arriving from orbit, from the edge of space, moving at a speed where the air molecules it collides with generate surface temperatures exceeding 3,000 degrees Fahrenheit on the vehicle's belly. The ship has to survive. That, fully intact, then flip from horizontal to vertical, then reignite its engines, then navigate itself to within centimeters of precision, then stop and be caught. The booster catch was historic. What is coming makes the booster catch look straightforward by comparison. SpaceX's Mechazilla system, the pair of giant mechanical arms attached to the orbital launch tower at Starbase in South Texas, successfully demonstrated the booster catch for the first time on October 13th, 2024. Flight 5 of the integrated Starship system launched at 7:25 in the morning Central Time, and 7 minutes later, the Super Heavy booster came back down and was snatched out of the sky on the very first attempt. SpaceX launch commentator Kate Tice called it a day for the engineering history books. Her colleague, Dan Huat, watching live at the launch site, said what they had just seen looked like magic. Astronomer Jonathan McDowell, one of the most respected independent space observers in the world, admitted he had not expected it to work. It worked perfectly. First try. Since then, SpaceX has made the booster catch look almost routine. What was once unthinkable has become a repeatable demonstration of precision autonomous flight. And that success is exactly what makes the next challenge so significant. Because catching the booster is catching something that never leaves the lower atmosphere. The Super Heavy first stage never reaches orbital velocity. It goes up, separates, and comes back. The heat loads it faces on return are manageable. Its flight computers are working with a relatively benign re-entry environment. It is an extraordinary engineering achievement. But the ship is something else entirely. The Starship upper stage goes all the way. It punches through the atmosphere, reaches orbit, and travels at speeds that no landing leg system, no drone ship, and no traditional ground-based catching mechanism has ever been designed to receive. When it comes back, it descends belly first, presenting its heat shield tiles to the incoming atmosphere. The tiles, the aerodynamic flaps, the structural joints between the flap actuators and the vehicle body, all of it has to survive re-entry before the catch can even be attempted. On Flight 5, while the booster was being caught at the tower, the ship completed its own re-entry and made a soft splashdown in the Indian Ocean. Cameras on board captured the reddish glow of heat building across the belly of the spacecraft. Engulfed in a fireball, the vehicle came through intact. That survival was itself a milestone that should not be overlooked. But surviving re-entry and making a controlled ocean landing is the prerequisite, not the goal. Elon Musk has been explicit about exactly what the prerequisite looks like. He stated publicly that SpaceX will not attempt to catch the ship with the Mechazilla arms until the vehicle has demonstrated 2 flawless, controlled, soft ocean landings, not 1. 2. And both of them have to be clean. The reasoning behind this is not caution for caution's sake. It is the specific logic of protecting the most critical and most expensive piece of ground infrastructure that SpaceX operates. If the ship comes in at the wrong angle, too fast, or with a guidance error. At the moment of the catch attempt, the result is not just a lost vehicle. It is a collision with the launch tower itself, and a damaged or destroyed launch tower sets the entire Starship program back by months. 2 demonstrated ocean landings establish a baseline of confidence that the vehicle's terminal descent behavior is repeatable and reliable before the tower arms close around it. This is the same disciplined approach that shaped the early Falcon 9 program. SpaceX did not attempt to land the Falcon 9 first stage on a drone ship until the booster had proven it could survive the descent environment. They did not attempt to land at the launch site until the drone ship landings were reliable. Every step in reusability was preceded by a demonstration of the step before it. Musk is applying exactly the same logic to the ship catch, but the stakes are higher because the vehicle is larger, the energy involved is vastly greater, and the ground infrastructure it is returning to is irreplaceable. So where does the program stand right now? Flight 12, the first mission to use the new Starship V3 hardware, is targeting launch as early as May 2026. Booster 19, the V3 Super Heavy, has already completed a full 33 engine static fire at Pad 2, the brand new second launch complex at Starbase that was rolled out to the orbital launch mount for the first time on April 11, 2026. Ship 39, the upper stage paired with booster 19 for Flight 12, has completed cryogenic pressure testing, the critical structural verification step that every vehicle must pass before flight. The FCC permit data, which SpaceX files ahead of every launch, shows that Flight 13 already has a permit dated May 29, 2026. That is an astonishingly rapid cadence between missions. The V3 is not an incremental update. It is a rebuilt system. The Raptor 3 engine, powering the V3 stack, is a ground-up redesign. SpaceX described it as simultaneously simpler and more powerful than its predecessor, with the complex heat shielding that caused significant maintenance headaches on earlier Raptor versions eliminated entirely. In December 2025, SpaceX released footage of a Raptor 3 running for 6 minutes and 40 seconds continuously, directly simulating a complete Starship V3 ascent burn from liftoff to main engine cutoff. That kind of sustained endurance run gives engineers the confidence they need that the engine can complete the full mission without surprises. No other engine in the world has been publicly demonstrated at this power level with this duration on a single continuous test run. Pad 2 doubles Starbase's launch capacity in a single edition. With 2 functional orbital launch mounts, SpaceX can theoretically prepare and launch 2 entirely independent Starship stacks simultaneously, or run back-to-back missions from alternating pads in a cadence that was previously impossible. This is not an abstract ambition. The infrastructure is there. The hardware is there. Flight 12 and Flight 13 on the same pad within the same month is the operational proof. Musk has said the first chip catch attempt will most likely come between Flight 13 and Flight 15. The variable is how the V3 flights perform. If both missions deliver clean, ocean splashdowns with consistent terminal descent behavior, the engineering team will have the data they need to authorize a catch attempt. Musk framed the window honestly, not as a promise, but as a probability range contingent on real-world results. Now consider what actually happens mechanically when the ship catch occurs. The vehicle descends vertically after its engine burn, approaching the tower. The chopstick arms are extended and positioned to receive the vehicle at a specific set of attachment points located under the forward flap structures. As the ship arrives and nullifies its remaining velocity, the arms close around those catch points and bear the full weight of a 165-foot rocket stage. There is zero margin in the lateral alignment. If the vehicle arrives even slightly off-center, the arms either miss or make contact at a structural point not designed to absorb the load. The vehicle's autonomous guidance computers, working from onboard sensors and ground-based tracking systems, have to execute this without a single error at the moment of contact. And they have to do it after the vehicle has just survived orbital re-entry, meaning the hardware must have functioned correctly through the most thermally and aerodynamically violent environment any object can pass through. The engineering precision this requires is qualitatively different from anything the catch system demonstrated with the booster. The booster arrives from a controlled hover with relatively low residual velocity and has never been through anything comparable to orbital re-entry. The ship arrives after surviving conditions that would have destroyed any previous generation of spacecraft structure. Successfully catching it means trusting that every tile, every flap actuator, every guidance sensor, and every propellant system on the vehicle worked correctly through re-entry and is still functioning accurately enough to navigate to within centimeters of the tower arms. That trust is exactly what the 2 ocean landings are designed to build. For the space exploration program beyond Starship itself, the ship catch closes a loop that nothing else in current development can close. NASA's crewed Artemis lunar lander is a modified version of Starship. The orbital refueling architecture needed to fill that lander. Before a moon mission depends on multiple Starship tanker launches. The faster a tanker Starship can be turned around between flights, the faster the propellant. Depot in orbit reaches the level needed to send astronauts to the moon. A ship caught at the tower is back on the launch stand immediately. A ship that splashes down in the ocean requires recovery operations, transportation, and full refurbishment before it flies again. The difference in turnaround time between the 2 scenarios is the difference between weeks and potentially hours. For a program trying to support sustained human presence on the moon and eventually send fleets of ships to Mars, that difference is not marginal. It is everything. Musk's stated vision of launching Starship multiple times per day from a single pad is only geometrically achievable if the entire recovery architecture eliminates transport time. Mechazilla was always the answer to that requirement for the booster. The ship catch is the answer to the same requirement for the upper stage. When both stages are being caught routinely, the only limit on launch cadence is the time needed to inspect, refuel, and restack. And the explicit design goal of the V3 system, with its simplified Raptor 3 engines and reduced maintenance requirements, is to make that inspection and refurbishment cycle as short as physically possible. SpaceX released a 3-year retrospective mini-documentary ahead of the V3 debut flights. Industry analysts noted that SpaceX does not release polished long-form content when a program is struggling. The release of a celebratory documentary at the precise moment Booster 19 has completed its static fire, Ship 39 has passed cryo testing, and Pad 2 has received its first full stack is a deliberate signal. The team knows Flight 12 is close, and they know exactly what it represents. When the ship catch attempt finally comes, it will be unlike anything any camera has ever recorded in the history of rocketry. A vehicle that launched from this planet reached orbital velocity, survived temperatures that would vaporize ordinary steel, flew back through the atmosphere as a controlled fireball, reignited its engines in the thin air above the launch site, and then descended with machine precision into the arms of the tower it left from. The same tower, the same arms, minutes or hours after the same vehicle was in orbit. The booster catch was historic. The ship catch will be the moment that closes the argument. Every question about whether full, rapid, complete reusability of an orbital-class rocket is physically achievable will be answered in a single sequence of events that no engineering team anywhere has ever produced. And when those arms close around the ship for the first time, what the cameras capture will not just be a rocket being caught. It will be the opening act of an era in which the cost of reaching space and everything that flows from that cost changes permanently and forever. History is not watching. History is already being written, and the most defining page of it has not arrived yet. There is one dimension of this story that even dedicated space enthusiasts rarely pause to fully absorb, and it is the dimension that separates what SpaceX is building from everything that preceded it. Every single orbital-class rocket in history, from the Soviet R-7 that launched Sputnik to the Saturn V that carried Apollo to the moon, has been expendable in whole or in part. The Saturn V cost the equivalent of over $2 billion per flight in today's money. Manufactured, flown once, destroyed. The space shuttle was partially reusable, but its massive external tank was thrown away on every mission. Booster recovery required such extensive refurbishment that cost savings were smaller than expected. No system before Starship was designed from the ground up to recover and reuse every component of the entire vehicle, including the part that actually reaches orbit. The numbers make the transformation concrete. Falcon 9 cost approximately $67 million per launch, with the upper stage expended on every mission. Starship, once operating in the fully reusable configuration the ship catch enables, has a stated long-term cost target below $10 million. With a vehicle carrying 150 tons to low Earth orbit, the cost per kilogram drops to a level the entire aerospace industry is still trying to comprehend. Every space application held back by launch costs moves from theoretical into the planning phase. Not a better rocket, a different economic reality. The ship catch is the keystone of that pathway. Without it, Starship is a partially reusable rocket that is better than what exists. With it, Starship becomes something that has never existed. A fully reusable orbital transport system operating at a cost and cadence the industry has never seen. The difference is not one of degree, it is one of category. So when the moment comes, and the cameras show the ship descending toward the Mechazilla arms for the first time, remember what you are watching. You are watching the closing of an argument that has been running since the dawn of the space age, about whether fully reusable orbital spaceflight is even achievable. The arms will either close or they will not. And either way, nothing about space exploration will look the same as it did before that moment.